On Friday, we reviewed the beginning of exponential functions, and you had to see kind of the rules that we used to apply with exponentials, such as the multiplication rule, the division rule, taking a power to a power, and being able to simplify. In calculus, exponential functions serve an important role because they allow us to look at the bigger picture. They allow us to look at exponential growth and decay. They allow us to look at applications, and they allow us to look at the number e. So in here, we will look at the growth and decay models and talk about their importance. So before we can look at the growth and decay models, it's important to understand exponential functions. So A is the base of an exponential function. If A is a number, then we can only combine it with other similar numbers. A has to be a positive number in order to show growth. The domain of an exponential function is negative infinity to infinity. The range is 0 to infinity, not including 0. So the domain is all reals. The range is 0 to infinity, not including 0. Examples of exponential functions in the real world are growth and decay of population, bacteria, compound interest or investment accounts, a growth model will go from something relatively small to negative infinity. So our growth model in this example is y equals 2x. So it's a doubling problem, meaning that every time you look at something, it doubles. So 2 to the 0 is going to then double when you look at 2 to the 1. It'll double again when you look at 2 squared, 2 cubed, etc. So if you think about the powers of 2, that's like going from 2 to 4 to 8 to 16 to 32 to 64, etc. An example of decay. So decay functions occur if your A value is between 0 and 1. So decay occurs if your A value is between 0 and 1. This is the graph of y equals 2 to the negative x. So what that means is that's really like looking at 1 to the 1/2 to the x. So there you can see that your A value is between 0 and 1. So again, if you're putting any key pieces of information on your notes, you would want to make note of the fact that decay is an A value from 0 to 1. The graph will be an inversion of an exponential growth, or as you can see, it goes from something relatively big to relatively small. These are the rules we went over on Friday, just reiterating and reviewing. If you have A times A, you add the exponents. If you have A to the x over A to the y, you subtract. A to the xy means you multiply. A times B means you distribute. And A divides B means that you distribute via division. So again, just seeing your notes from day one. So the model we're going to really talk about today is an exponential growth and decay with a K value. So what I want you to do now is take out your graphing calculators and we're going to graph 4 to the x minus 3. So we're going to graph 4 to the x minus 3. So you can see an example where you have an a to the x and shifting its function. So again, use your graphing calculator to graph 4 to the x minus 3. So when you graph this, it asks you to find the zeros. Remember, the zeros are the x-intercepts. So what that means we're looking for is the points at which this graph crosses the x-axis. So in this case, there is an x-intercept here. On your graphing calculators, you can hit second trace. And when you hit second trace, you're going to go over to the 0 option. So you'll hit second and trace. Go down to option number 2, which is 0. And then you're going to enter the left bound. So the left bound would be over here in the navy blue region. So you're going to hit enter so that your graph is somewhere to the left of our x-intercept. You're going to arrow to the right so that my graph is to the right. After you do your left bound, you do your right bound. Your right bound needs to be somewhere in the orange. Hit enter again. The third enter is your guess. It means nothing. You can literally hit enter where you hit enter for the right bound. And then what should happen is you see that your 0 is at 0.792. So remember, everything in calculus is 3 decimals. So your 0 or your answer is 0.792. So when I ask you to find the zeros of that function, your answer is 0.792. If I asked you to describe the transformations, the -3 tells me what about this function? Brooke? Exactly, it was shifted down 3. What would that do to the range of this graph? So if the range of a normal exponential is 0 to infinity, what's my new range, Brooke? Yeah, it would be -3 to infinity, not including that -3. Does my domain change? No. Still -infinity to -infinity. One of the ways, so again, your note packets, there's just an extra page. I copied 1-3 twice. Sorry about that. So you're jumping over to the next page. So you can just put a big X on that second page. It just copied it twice. You don't need it. So half-life, an exponential function is used in science to help determine half-life. So radioactive substances have a half-life property that is significantly important. So we can look at exponential functions to model the phenomena that produce this decrease over time. So the half-life of a radioactive substance is the amount of time it takes for half of the substance to change from its original radioactive state to a non-radioactive state. So that's like Chernobyl there's the whole movie about it, and they talk about not being able to go in because all of the people were infected by radioactive activity. So we're waiting for it to be a safe area. We can talk about it with substances. So it says modeling radioactive decay. Suppose the half-life of a certain radioactive substance is 20 days and that there are 5 grams present initially. And we want to find out when there is 1 gram remaining. So we have a particular formula that we're going to talk about. And that formula is a variation of this formula here, the y equals k times a to the x. So when we talk about half-life, we're going to use a variation of that y equals y naught. So the y naught is your k, a to the x. So go back and kind of think about, what does the word present initially mean? Something is initially present. What does that tell you? Yeah, go ahead, Brooke. Yeah, it's how much is there at the very beginning. Good. So which of these parts would kind of represent what's there at the very beginning? Go ahead, Brooke. Yeah, the why not, right? That why not's going to represent what's there at the very beginning. So what's there at the very beginning? Well, what? Yeah, the 5 grams. What am I looking for? I'm looking for when there's how many grams? Quick you? 1. 1. I'm looking for when there's 1, not the half-life. We're looking for 1. So the half-life is 20 days. So that does have an important part, but that's going to give me the 2.5. You're saying this is what I'm looking for. So in order to find what I'm looking for, we're going to use that idea of half-life. So 2.5 is equal to 5 a to the 20. Because the x represents the days. We know that half-life happens after 20 days, so we're looking for my a value. So we'll divide both sides by 5. So you have 2.5 divided by 5. So you get a half equals a to the 20. So how do I get rid of something to the 20th power? Yep, we're going to raise it to the 1/20th. So you take 0.5 to the 1/20th. And we get a equals 0.9659. So 59 would round to 6. Now we're going to go back and solve for x that we know a. So we have 1 equals 5.966 to the x. So obviously we need a calculator. What's one way we could do this on a calculator? I could put 1 into y1, and I could put this equation into y2, And then I could look for their intersect. So that's probably the easiest way to go about doing this. So what you're going to do is in Y1, you are going to plug in 1. In Y2, you're going to plug in the 5.966 to the x power. So on your initial graph, unlike zoom standard, we see that they don't quite intersect. So you're going to have to zoom out or change your window. So maybe I make my x min 0 and my x max 50. And then I'd go to second trace. And now you're going to go to option 5, which is intersect. And you'll move to the first curve where you think they hit, the second curve where you think they hit, and then you guess. And we see that their point of intersection is actually at 46.527. So what that means is it takes 46 and a half or 47 days to be at 1 gram of substance remaining. Takes 47 days to get to 1 gram of substance remaining. Okay, so staying on those graphing calculators, exponential regression is an important part of calculus as well. So what I want to do is go back and kind of look at how to use our calculators using exponential regression. So go ahead and take out that grapher again, hit stat this time. You're going to go to edit. There might be data in your grapher. Just hit clear on L1 and L2. So when you hit stat, edit, and clear, you want your graphing calculator to have nothing on L1 and L2. And then we're going to enter in our data. So be careful. It says using the population data below, estimate the population for the year 2000. Compare the result with the actual 2000 population, which is approximately 281.4 million. When modeling the data, let x equals 0 represent 1880, x equals 1 represent 1890, and so on. So when you enter your data in L1 and L2, you are not entering 1880. You are entering 0, then 1, then 2, then 3, 4, 5, etc. I believe there's numbers on the next page too. I think one or two rows got copied to the back. So you should have 0 to 11. And we are looking for 12. So in order to find exponential regression, you enter your data in the stat and edit. Then go back to your home screen, hit stat, arrow to the right over to calc. And then you're going to go down to option number 0, which is exponential regression. Hit enter. You want L1 and L2 to be in your list. Go to calculate. And you should be able to get the equation that y equals 56.469. And again, they say you can truncate. You don't have to round. If you rounded, you would have to make it 0.47. 1.152. So if you do round, it's okay. Again, AP says truncate 3 or 4 to the x power. And then our goal is to find the value when x equals 12. So you're going to take that same equation and plug in a 12. And you get 308.26. Yes. To get exponential regression. So you hit stat and edit, you enter your data into L1 and L2, go to your home screen, then go back to stat, arrow over to calc, and then you have to go all the way down to EXP regression, which is option 0. Did you make sure you have data 0 to 11? Because there were 2 pieces of the table on the next page. Okay. So is our exponential model an overestimate? And if so, by how much? So if you recall percent error from chemistry, did you do percent error in physics too? Where it's like actual minus experimental all over. Okay. Is it up there now? I like went away. Okay. So let's go ahead and find that. So our actual was 281.4. Our experimental is 308.261 over the actual times 100 to find a percent. And we have an overestimate of 9.545%. And in case you forgot, it's the absolute value of the numerator. All right, so we have the infamous number e. E is an irrational number. It is an exponential phenomena that occurs in lots of physical and economical aspects of the science world. It is an actual function, if you never knew that. E is actually a function, and it can be represented using the equation up on the board. So E is actually a function that occurs when you have f of x equals 1 plus 1 over x to the x power. And we look at it as x is going to infinity. We're going to talk a lot about x approaching infinity because that is a large part of limits, which is coming next in chapter 2. Sorry, do you need the equation still? There you go. You're okay. Okay, so we have the exponential function y equals e to the x and y equals e to the negative x. These are frequently used models for growth and decay. Does anybody remember using Pert? Maybe last year? Not at all. Okay, so Pert is an interest compound formula where P represents the initial amount or your initial investment. So it's kind of like the why not in our Halflife equation. R is the rate at which you're investing. And then T is the time in years that you invest. So right now, those interest rates are really low because of the pandemic. So investing right now is not the best. Do you want to go buy a house or a car?
Camry Andrews, please come to the office. Camry Andrews, please come to the office.
So again, like I said, exponential functions are used a lot with growth and decay. So we're going to actually look at a real world example with exponentials and something I'm sure you've all experienced at some point in your kitchen. So we have fruit flies. Fruit flies are pesky little things that once you get one, it feels like you have a ton of them. So what we're going to do is kind of look at this example. So it says the approximate number of fruit flies in an experimental population is given by that equation right there. The QT equals 20e to the 0.03t. So what does the 20 represent? What does the 20 represent? The 20 is the initial population or number of fruit flies. So part A says, tell me what does that 20 represent? So at time t equals 0, you plug that in, you simplify, you get e to the 0, which is always 1. E to the 0 or anything to the 0 is 1. So we get that the initial population is 20 flies. The initial population is 20 flies. Part B, how large is the population after 72 hours? So what you want to do is plug 72 into that equation. So you're going to find Q of 72. So again, if you're still working on plugging into your graphing calculator, this is where you would plug in 72 for t. Now, my answer here is rounded and not in decimals. It is rounded because we are talking about a population. I can't have a fraction of a fly. Cannot have a fraction of a fly. So you'll notice that I did not put equal signs. I put the approximate because you cannot have a fraction of a fly. So we approximate it, how many? And then to see what this looks like, we can see exactly how quickly that function is growing. So you'll notice that the population of fruit flies in a really short amount of time increases. When something increases a lot in a short amount of time, we call it exponential growth. Questions at all on exponential growth models or decay functions? Okay, then we're going to work on problems in the book. You're looking at 1 to 18.